Hi everybody, thanks for taking the time to view this short video today. My name is A.J. Meceli. I'm from the PSSI Global SATCOM Division, headquartered in Orlando, Florida. My name and number are on the bottom of this page so you can email or call me with any questions you might have. Today we'll talk about amplifier linearity. Looking at our first plot, we see that the spectrum analyzer is set for a span of 100 megahertz. That's going to be 10 megahertz per division. This is an 18 megahertz carrier at a very low input power, negative 35 dBm. As you can see, the noise floor is about just shy of 2 dB off of this neg 60 mark. The carrier is at the neg 50 mark. If you subtract 50 from 62, you'll get roughly what this number is, 11.67. Now this is very low power. It is not a good carrier to noise because it is very low power, but I need everybody to understand the relationship as we go through these slides. Okay, this plot shows that we increased our input by 5 dB. The first slide was a negative 35, this is a negative 30 dB. Essentially, you're linear as long as you raise the input by 1 dB and you see an output that's greater by 1 dB, then you remain linear. The carrier is rising, the noise floor is not. In this case, we've got a negative 30 input, and if we look at the figure here, we've got a neg 17.27 carrier to noise between this point and this point. And that relates to 6.3 watts. The first plot, we had 2 watts. So our carrier to noise is increasing, everything is looking good. In this plot, we've increased our input level to a neg 25 dBm. As you can see, the noise floor has not moved, but yet our carrier to noise has increased. This looks really, really good. This would be an excellent carrier to noise. 21.4 would be just fine. Now we've increased our input by another 5 dB. So we've got a negative 20 in. That gave us a 48 dBm output, or 63 watts. And look at our carrier to noise, almost 24. That's just about perfect. You can also see the noise floor is just starting to come up, less than a dB here, but it is rising. At a point, the noise will rise and the carrier will rise equally, and then you get to compression where the carrier does not rise and the noise floor continues to rise. Okay, so we raised the input power by 2 dB now, from 20 to neg 18, and now look what's happening. We've got a negative 26.42 carrier to noise, also excellent, but we can now really see the noise floor starting to rise. I would say this is a 350 watt TWT amplifier, by the way, KU band, and I would say this is probably the most linear that this amplifier is going to get. And right now, a 26.42 carrier to noise is excellent. We're putting out 100 watts out of this 300 watt amplifier. It all looks good. Now we raised the power 2 more dB to a neg 16. Look at the result. Now we're at a negative 24.68, which is less than the plot we had before, which was a negative 26.42. So we're losing carrier to noise. And you can see this because look at the noise right here climbing up. This is 10 dB per division, so it's climbing up 2.5, 3 dB right here at this point. And that can be noted here in your total carrier to noise being reduced by the same amount. Raising the input level another 2 dB to a minus 14 on our modulator, we're getting an output power of 251 watts, but we are above our linear range. Take note, here was our noise floor. It's up a little bit better than 10 dB. Your carrier to noise has been reduced to 19.96. At this point in time, what you have to remember is these shoulders, or what we used to call shoulders, may be on the other transponder on the opposite side, but it is injecting noise into the signal. Furthermore, you may not realize it, but it has also reduced your signal to noise off of this carrier because the noise is now so high. It's mixing noise with your signal, so your EBNO on your receiver is going to decrease. This is far too much power. you're above the linear range, and going any further, you could damage this amplifier, especially if it's a tube amplifier. Once again, at the neg 18 input, this was perfect. This was a perfect carrier to noise, 26.42. Everything looking good here. No distortion. Should be an excellent feed. This one, not so much. So let's review a couple of definitions. The saturated power of an amplifier is when the tube is saturated with signal, and it will only make so much power. Once you reach that point, it's called saturation. Rated power is different. Rated power is taken after the output waveguide arm. There's filters, there's directional couplers, and there's a little bit of loss in that. So rated power is going to be a little bit less than saturated power. But that linear region that we looked at is way below even rated power output. Gain compression, of course, is the point at which the amplifier becomes totally nonlinear, and a 1 dB increase in drive power does not result in a 1 dB increase in output power. Every amplifier has a maximum input level, whether it's a tube amp or an SSPA or an SSPB. When you overdrive the input of an amplifier, it causes damage to the front end. If it's an SSPB, there's a buck on the front end, you could damage that block-up converter. If it's an SSPA, then the very first thing you hit is one of the SSPA devices, and you could damage one of those. If it's a tube, the same thing can happen. You can overdrive a tube, you can damage that tube, you can corrupt the filament or the helix. So it's really important to know and to realize what's going on as you raise your input power to these amplifiers. So if you need to go back and look at these slides one at a time, or maybe the whole presentation one at a time, it's easy for you to see in this environment. Unfortunately, our engineers do not have the test equipment to be able to do this in the field and to actually see this in the field. So that's why we have this presentation today. We're going to do a couple of more presentations with calculating dB and watts and back and forth from watts to dB. But for today, this is it on amplifier linearity. Thank you.